So today we have a very interesting topic to talk about, and this is AI-assisted performance feedback in API programming. Right. So let me start this discussion by defining the main use case that we are going to be focusing on today. Now, as you know, APIs offer a simple way to programmatically interact with a separate software component or a resource, right? Now, one of the main reasons why we use APIs is that they hide the underlying implementation and only expose the objects and actions which the developers needs to focus on. Now, when it comes to creating a new API, what you usually do is you create a new API by combining set of other APIs. And then this new API will be consumed by various parties, right? So our main focus today is a developer comes to an iPaaS like cloud platform and start developing these API programs, right? So the iPaaS stands for Integration Platform as a Service. It is a collection of cloud services which allow you to develop, execute, govern, and govern integration flows between disparate applications. Our goal is to see if we can estimate the performance of these API integrations or API programs which the developers are developing at the development time, right? So this is a development time user experience that we are talking about. Right. So a little bit about iPaaS. So you might wonder why people use iPaaSes. One main reason is that they eliminate the complexity of building and maintaining your own servers and infrastructure, right? And the iPaaSes are supposed to be cost effective. So therefore, there's no operating costs. And also they have various tools that allow you to develop your applications faster, such as low code like IDEs, AI assisted development tools, such as the one that we are talking about today. And also the other important aspect is the scalability, right? Now, as you know, if you are to run these applications on your own infrastructure, you will run into scalability issues at some point in time. Now, if you run it on an iPaaS, on the other hand, it is all taken care of, and basically it will auto scale as the load increases. So the last aspect is the security. So the security is of course there by default. So you don't need to do anything additional to sort of satisfy your security requirements, right? Okay, so let me now give you a sort of a feel of the type of use cases or programs that we are going to be focusing on today. So let me actually show this using IDE directly. So I hope you can see this screen. So I have changed this screen to something else. Now, so remember now, so the user comes into a cloud platform and then he logs into that cloud platform and then he develops this integration program. So this is an IDE of that cloud platform, right? So as you can see on the left hand side, so this is called the Choreo. So the Choreo platform is a next generation iPaaS which we are building right now. So this is going to go into GA very soon. So I'm not going to talk about the details of that. If you're interested, you can Google it and figure out the details. Now, so basically there is a low code diagram. So you can develop this integration application using the low code, or you can use the full code. So both options are there, right? Now, so this particular use case, which I want to, so this is just one of the examples. You are building a use case and you want to compute the COVID-19 cases per million people in a particular country. Okay, so now if I'm to show you the program, so let's keep the low code aside and focus on the code here. Now, as you can see into this program, you pass the country code, right? So, you want to get the COVID-19 cases per million people in a particular country, right? And then basically it does this, it mainly, performs two API calls, right? So it is actually these two. Now let me describe, these ones. Now, first thing you do is like whenever you make an API call, you have to create a client object, right? So here we are, creating the COVID-19 client, and then using that client object, basically you invoke this particular. You basically have this, you call this the action, right? And then you get the basically you get a collection. So in that particular collection, you have the number of COVID-19 cases, so total number of cases. And then you make another API call because you need to get the population also, right? You talk to a different endpoint using a different client object. So this one is actually the World Bank client. Then you get the population in that particular country. So that's another API call, right? And of course, then you'll have to divide it by 1 million. And then using these two, you can compute the total cases per million people in that particular country, right? So basically, this is an example of an integration, program or an application, which the developer would be writing sort of an iPaaS platform, right? So let me now go back to the main presentation and then do the slide share. Right. So before going into the details, now our objective is to basically see if we can provide the performance estimate for that particular program as the developer is implementing it, right? So before getting to the other details, let's talk a bit about the performance. So why performance? Now, performance, as you know, is one of the most important non-functional requirements, right? So it has a direct impact on the user experience, right? Also, poor performance can, cause customer dissatisfaction, and it can lead to even customer churn. Now, typically these API programs, they handle large volumes of requests. So you're talking about like high throughput cases. The performance of these API programs depends on two main things. The first one is the incoming workload. So that means like how many users are accessing this particular service or the API, and message size, the arrival rate, and so on. So there are various factors, which impact the performance and the program characteristics. Now, one main thing to note here is that for these sort of, programs, what impacts the performance the most is these network interactions. Now, in the previous example, which I showed you, you have seen two API calls going out, right? The processing in the service is usually minimal, right? So the performance impact of that, is not that significant for these type of, API programs. So then, okay, so then the next question is, why do you, what is the benefit of estimating the performance? So there are multiple reasons. First is that, you are developing an API, and if you have a certain SLA, right? Now, without even running this particular service or the application, you see whether that SLA is satisfied, right? Because if the estimate is accurate, you can test it. And then also another important point is that if there is a performance related bug in your code, right? You might have written a for loop, and in that particular for loop, you're accidentally calling, API multiple times, right? So then this would be immediately, visible to you, because you will get the performance degradation. You will see that there's a performance degradation, and then you can go and fix that bug. Also, you can understand the scalability behaviors as the load increases, or how does the, for example, throughput and the latency vary. So also another use of this is that usually developers, at least to some level, they have to run performance tests, right? I mean, in certain companies, of course, there are other teams, but now this could develop, development, can save developers time. Okay, So now there are two performance metrics that we are focusing on today. So actually these are the two main ones anyway. First one is the throughput, right? So the throughput is the rate at which a service or the microservice or a system is processing requests, right? So the usual behavior is that as the load increases, the throughput increases sort of linearly, and then it sort of becomes a constant, and then it starts to degrade, right? So when it starts to degrade, you call that the system has gone out of the steady state. And the other important metric is the latency. Now the latency is actually, it's not a single value, right? So there's many, when you do a test, you get a lot of latencies. So you say that the latency exists in a form of a distribution, right? So these distributions can be of different forms. So typically these distributions are sort of skewed, right? So from this latency distribution, then you can compute, various statistics such as 99 percentile or the average latency, 99.99 percentile, and so on. So, and then you can also investigate how these statistics vary with the concurrency or the load, right? So in this particular case, we have the average latency, and the y-axis, x-axis is the load or the concurrency, right? So you can see as the load increases, basically, the latency increases linearly, and then it starts to increase a bit faster, and then it starts to increase exponentially. So that is the stage where the system has gone out of the steady state, right? So basically our objective is to see if we can estimate these two curves for this particular API integration which the developer is building, right? And then provide those as feedbacks in the development time, right? So the way we do this is that we represent this API integration as a queuing network or a queuing system. So queuing theory is used extensively for computer systems performance analysis. So this is actually one way to do it. So there are different other approaches also. So each component in this integration, we represent it as a server. So these servers consist of a queue and a processing element. So in this case, so this is a closed system queuing network. You have the workload generator. So this is the client, right? The guy that sends a request to the API program. And then you have the integration application. This is what you write, the one in the middle, right? And then it does API calls. So those, those endpoints also we basically represent as servers, right? So if I'm to explain the flow of, request, so you get a request into the API, and then, okay, if you map this back to the use case on the left-hand side, then it sends a request to the COVID-19 endpoint, right? That is the first thing that it did. And then it gets a response back. So that is number 3. And then it sends another request to the World Bank API, that is to get the population of the country. And then it gets a response back, number 5. And then it sends the response back to the client, right? So that is number 6. So this is the flow of messages for this particular use case. Okay, so how do you estimate the performance, right? So the way we do this, so this is, again, this is one way to do this, is that for this external sort of endpoint, we build separate models, okay? Separate models, and using these individual models, we compute the performance of the integration application, right? Now, so what is the data that we need to build these models? So basically, one is the latency for that particular, action invocation or the API call, and the number of requests in progress. So those are the two main parameters that we are measuring right now. Of course, these can be extended to, to make it more complicated than, but yeah. So, and then we do that for the second one also. So there's also second API. right? And so that is the data that we collect. Now, how is this data collected? So the iPaaS, this cloud platform, of course, it has an underlying observability platform, right? So what we do is we instrument the these API programs that are deployed in production. We instrument them and then collect the data. So there will be multiple of these applications running in the cloud, right? So then these data will get pushed. Now here we have a message queue. I mean, this architecture can be quite flexible. And then we store this data in a data storage, then periodically train set of models for each of those API calls, right? So that is the training flow, right? So then, of course, now this is an example, like this is some data which is collected from one of the APIs. So basically, I mean, this, by the look of this, it is actually, it's kind of like a very much linear, but usually these patterns are non-linear, right? So this is for a particular endpoint. Now, as you can see, so to build those individual models, there's multiple ways, right? You can fit an analytical model, such as universal scalability law. So that is a way to analytically model the scalability characteristics of a system. It's a black box sort of an approach where you you have the output, which is the latency or the throughput, and then the load, and then you fit an analytical model, and then you can use that model to derive the performance metrics that you want. Or you can even go with the machine learning approach. You can fit something like you can train an XGBoost model and then use that model to get the performance numbers that you want, right? Now, so what happens is that so basically now the developer is developing this application. Now we want to provide this performance estimate. What we do is we pass the program. Basically, there's an AST. From the ASTs, we extract these API calls. So these are the ones that actually impact the performance the most, right? And then basically we solve another set of equations. This is solving for the integration application. And that set of equations use those individual models which we have trained, right? So that is the basic idea behind this. And then by solving that one, you can then get the performance of that application, right? So that's the basic idea. Now, so these are some accuracy results. So we have compared the actual and the estimates. Now, as you can see, they are pretty close for certain concurrencies, but it could deviate as well. Now, the deviation happens because of lack of data, but in cloud platforms, usually you get a lot of data, then these values will improve as the time goes, right? So let me now stop. Let me now go to the IDE and then, oops. Right. So this is the program I showed you earlier. So basically, if I click on this, I should get the performance forecast. Right. Okay. So basically what it shows is, so this particular, integration, these are the performance curves. As you can see, you can click on a point, and then that would show you the latency and throughput values for that particular concurrency, right? So basically, and then you can even go to the code, and even in the code, you can see so this is the total concurrency and the latency. And then if you click on it, you get the breakdown, right? You can see that for this API call, that's gone for some reason. For this particular API call, it takes 20 milliseconds. And this particular one, it takes 35 milliseconds. In the low code diagram also, you can, you should be able to see the breakdown. Yeah, so you can see the breakdown. So let me go back to the presentation slideshow. Right. So today I presented the idea of providing performance feedback for API programs at development time. So we think this is something very useful due to a number of reasons. First is that, you can check if your SLAs are satisfied, and then you can, check if there's any performance related bugs, then you will see a performance degradation, and then you can go and fix those bugs. You can understand the scalability behaviors and so on. So this was done by representing the API program as a queuing network, and then training set of models for individual interactions, and then finally solving another set of equations which uses those individual models, right? So that would bring us to the end of this session, and thank